I will explain you Borel Cantelli lemma in this video. This lemma you can see in the 5th unit of measure and integration. In fact, you are having two Borel Cantelli lemmas in measure and integration paper. You can see the first Borel Cantelli lemma in the first unit, and also you will have another Borel Cantelli lemma in the 5th unit. There is a small difference between these two. I will tell you what is the difference. The lemma present in the first unit you will use the measure m. Okay. Here you will use the measure mu. That's the main difference between these two lemmas. So let us start proving the lemma, Borel-Cantelli lemma present in the 5th unit of measure and integration. So here you can see the statement. First you have to consider a measure space. Let x, m, mu be a measure space. Here m is the script m. Okay. X denotes a set, m denotes the subset of the set x, and mu denotes measure. Okay. If you write all these like this, then you will say that as a measure space. And you are taking countable collection of measurable sets, that is this. Okay. And ek, k equal to 1 to infinitive, is a countable collection of measurable sets, for which there is a condition. When you find the sum of measure of these countable collection of measurable sets, the value will be finite. That is what the meaning of this. Okay, summation means sum. You are finding the sum of what? Measure of EKs. The value will be less than infinitive. If these conditions are there, then what we have to prove is almost all x in x. It means in x you are having elements, okay? That elements are denoted as small x. For almost all x in x belongs to where? To at most finite number of EKs. All elements x in x will present belongs to the finite number of EKs. That is what we have to prove. So before proving this, in between you will prove some other thing. Okay. Only after proving that you have to prove this main theorem, main lemma. The reason for proving that is you will use that in between proving this. Okay, so that is why. So here let us pass on to the proof. In the proof, first you have to write given this is a measure space. First you are going to, as I told you earlier, first you have to climb this equal to this. That is what we have to prove. That is, set of all x belongs to capital X. You have to write like this. X don't write like this. Okay, I forgot to write this. That is why have wrote like that. When you write, how you have to write a set of all x belongs to x such that x belongs to in. That is how you have to write. Okay, so set of all x belongs to capital X such that x belongs to infinite number of EKs is equal to this. That is what we have to prove. So first you have to consider this. Suppose x belongs to infinitely many of the EKs means what will happen? X belongs to all EKs. Okay. If x belongs to infinitely many of the EKs means x will present in all the EKs except finite number of EKs. It means x does not belongs to finite number of EKs. Okay, but x belongs to infinitely many of the EKs. Okay, but x does not because x belongs to infinitely many of the EKs, right? So x does not belongs to finite number of EKs. Therefore, from this you can write this. X belongs to infinitely many of the EKs, right? So that is from this line you are writing this. X belongs to union k equal to 1 to infinitive EK, comma n equal to the value of n varies from 1 to etc. till infinitive. Okay, because x belongs to infinitely many of the EKs. That is why x belongs to infinite number of EKs. That is what you are writing. Now here you have wrote x belongs to all EKs, right? It present in E1, E2, E3, E4. So it present in all the EKs, all infinite number of EKs. So that is why you are writing x. Then if it is presenting in all EKs means what? It will present x belongs to the intersection also, right? You can write like that. So that is why x belongs to intersection n equal to 1 to infinitive and write this. Okay, so at the first what you have took x belongs to infinitely many of the EKs and finally you got the same x belongs to the intersection value of infinitely many of the EKs also. So you can write this equal to this, right? So that is what, hence we obtain this equal to this. This is what you have to climb. So you climbed it. Mark it as equation number star because you will use this. This is the main part of this proof. You can see this part in your textbook. Okay, so this is the main thing. So for each n, by countable subadditivity of mu, you are using this proposition here. By this proposition, you can write this. This mu of this less than or equal to, you are bringing this union outside so that it is becoming summation k is equal to n to infinity. You are writing this by countable subadditivity of mu proposition. And the value of this is less than infinitive in the statement they are given you. But here you have to note something. Here you are having k equal to 1 to infinitive, this value less than infinity. Here you have having k is equal to n to infinitive. Here may raise a question, can we put that? Here this value is less than infinitive. Can you put this? Can we apply this here? There may be raising, you may raise a question. So here you have wrote for each n. For each n. Okay, for each n means what? In the place of n, you can put 1, you can put 2, you can put 3. Okay. So, you can apply this also. You can apply this here. Okay. Because for each n, because of that, you can write like this. For each means n takes the value 1 also. So, if you put 1 here, you can apply this here, no? So, that is by continuity of mu. Now you are using another one proposition, that is by continuity of mu, you are taking mu of this value is equal to limit n tends to infinitive this is, you are writing this by another proposition, by continuity of mu. Okay. Now from this you can write from this you can write this. How? You are writing limit n tends to infinitive as it is. Here you know that mu of this value can be written like this, right? That is how you are writing. Here inequality is less than or equal to. So that is why you are putting less than or equal to. Now the value of this is 0 because here n tends to infinitive. So if you put k equal to infinitive to infinitive. Infinitive to infinitive means you will get 0. That is how you are getting 0 here. Now you got left hand side is equal to 0. Okay. You know that the value of this. You already proved that this value. In the star, look at this. The same value. The left hand side, what do you have? X belongs to capital X such that X belongs to infinite number of EKs, right? So in the place of this, you are going to substitute this. You are going to write this. Okay. So mu of X belongs to capital X such that X belongs to infinite number of EKs is equal to 0. So now what you are getting, measure of X belongs to infinite number of EKs, you are getting 0. Measure value you are getting 0. So from this what you will get? So X belongs to, so from this you will come to know that X is not present in infinite number of EKs. Because the measure of X belongs to infinite number of EKs, you are getting 0. So from this you will come to know X is not present in the infinite number of EKs. So that is what you are writing. For almost all X in X belongs to at most finite number of EKs. It does not present in infinite number of EKs. It present in what? Finite number of EKs. Hence the proof comes to an end.